Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation. The paper titled OPENTAB, Advancing Large Language Models as Open Domain Table Reasoners, proposes a novel framework for open domain table reasoning tasks. This framework, known as OPENTAB, leverages large language models, LLMs, and is composed of several key components. 1. Table Retriever. The first component of the OPENTAB framework is the table retriever, which is responsible for retrieving relevant tables from a large corpus. The authors suggest using the BM25 algorithm for this task, citing its scalability and effectiveness. The BM25 algorithm is a probabilistic-based ranking function commonly used in information retrieval systems to rank documents. 2. Table Reasoner. The table reasoner is the second component of the OPENTAB framework. It processes natural language queries in conjunction with table schema and sampled rows. The table reasoner is composed of three main subcomponents. 2.1 Coder. The coder is responsible for generating SQL programs of increasing complexity. The authors propose a simple to complex prompting strategy for effective SQL generation. The coder generates three SQL programs with ascending complexities and functionalities. SQL Basic. This program focuses on column selection. SQL Intermediate. This program incorporates both column and row selection. SQL Advanced. This program empowers additional operations including, but not limited to, aggregation functions and text operations.
2.2 Reader.
The reader uses an LLM to parse and extract the final response based on the SQL execution results. It is provided with broader context from the coder, including table schema, sampled rows, and the generated SQL query. 2.3 Row Selector. The row selector ensures that the pertinent rows are provided to the LLM for effective processing. It uses the BM25 algorithm to re-rank and choose the top K rows based on their relevance to the query. 3. Generative Re-ranking and Sequential Reasoning, GRSR. To address the trade-off between retrieval recall and precision in open domain table reasoning, the authors propose a novel strategy called Generative Re-ranking and Sequential Reasoning, GRSR. GRSR sequentially generates SQLs for a set of retrieved tables and then re-ranks them based on query similarity. This strategy effectively addresses the hallucination issues often encountered in open domain table reasoning.
Experimental work.
The authors of the paper conducted a series of experiments to validate the effectiveness of their proposed open domain table reasoning framework, OPENTAB. The experiments were designed to assess the system's performance in both open domain and closed domain settings and to compare it with several baseline methods. Datasets. 3 datasets were used in the experiments. Open Wiki Table. This is an open domain table question answering dataset. Due to budget limitations, the authors randomly selected 2,000 samples from the validation set for their experiments. The corpus contains 24,680 candidate tables. Wiki Table Questions. This is a closed-domain table-based QA dataset that provides the relevant table containing the necessary information for each query. Feverous. This is a fact verification dataset that requires the identification of multiple relevant tables for reasoning and verifying factual questions. The authors adapted the dataset for open-domain table reasoning by filtering 323 examples from the validation set that relies solely on table data. Baselines. The authors compared the performance of OPENTAB with several baseline methods, including Binder, Dater, LLM Answer, and LLM SQL. Evaluation metrics. The primary metric for evaluating performance on the Open Wiki Tables and Wiki Table Questions datasets was execution accuracy, EA. For the Feverous dataset, a metric was adopted that demands the pipeline not only to make the correct predictions, but also to correctly identify the gold evidence tables for making those predictions.
Results.
The experimental results demonstrated that OPENTAB significantly outperformed the baseline methods in both open domain and closed domain settings. For instance, in the open domain setting on the Open Wiki Tables dataset, OPENTAB outperformed the best baseline with a remarkable 21.5% higher accuracy under the top 10 scenario. In the closed domain setting on the Wiki table questions dataset, OPENTAB outperformed even fine-tuned methods. Ablation studies. The authors also conducted ablation studies to validate the efficacy of the various components of OPENTAB, including the simple to complex, STC, SQL generation strategy, the row selector, and the reader module. The results of these studies showed that each of these components significantly contributes to the overall performance of the system. This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled LLMs in the Imaginarium, Tool Learning Through Simulated Trial and Error introduces a method known as Simulated Trial and Error, STE, for tool learning in large language models, LLMs. This method is inspired by the way biological systems approach tool use, which typically involves a process of trial and error, imagination, and memory. Exploration phase. The first phase of the STE method is the exploration phase. In this phase, the LLM interacts with a tool, for example, an API with its specification, to learn about its use. This phase consists of a series of trials, each of which involves the following steps. Imagination, the LLM imagines a plausible scenario for using the tool. Interaction, the LLM interacts with the tool to fulfill the imagined scenario. This is done by making an API call and observing the feedback from the tool. Self-reflection, the LLM reflects on the trial, considering whether the tool use was successful and what could be improved. The exploration phase also incorporates two memory mechanisms. Short-term memory, this consists of recent trial trajectories, which help the LLM learn from its successes and failures and explore the tool in greater depth. Long-term memory, this contains distilled past exploration experiences, which help the LLM progressively learn over a long time horizon. Exploitation phase. The second phase of the STE method is the exploitation phase. In this phase, the LLM uses the tool use examples from the exploration phase to improve its tool usability. This can be done through either fine-tuning or in-context learning, ICL. Fine-tuning, the LLM is trained on the tool use examples, with the loss computed only for the tool use response generation part. In context learning, ICL, the tool use examples are used as a demonstration pool. The examples that are semantically closest to the test user query are retrieved and used as in-context examples. Continual learning. The paper also explores the concept of continual learning, where new tools are continually added to the LLM's repertoire. This is achieved through a simple experience replay strategy, which allows the LLM to learn new tools while preserving its existing tool use capabilities. In summary, the STE method provides a comprehensive framework for tool learning in LLMs, incorporating exploration and exploitation phases, memory mechanisms, and continual learning strategies. The paper presents an experimental work designed to validate the effectiveness of the proposed method, Simulated Trial and Error, STE, for tool learning in large language models, LLMs. The experiments are conducted on APIs from Toolbench, a large-scale repository of real-world APIs. Experimental setup. The authors selected 50 APIs from Toolbench, which include search engines, domain-specific information-seeking APIs, and problem-solving ones. These APIs were chosen based on their free usage, low execution latency, and high quality. Exploration phase. In the exploration phase, the authors used ChatGPT for exploration and paraphrasing, and GPT for final example filtering. Each API was explored for 15 episodes with 4 trials per episode, resulting in a total of 60 examples before filtering and paraphrasing. After filtering, 15 examples for each API were randomly selected into the test set, and the remaining ones were paraphrased into approximately 140 examples. Exploitation phase. In the exploitation phase, the trials obtained from the exploration phase were utilized to enhance the tool usability of an LLM via either fine-tuning or in-context learning, ICL. For fine-tuning, the authors used the standard language modeling objective. For ICL, the synthesized examples were used as the demonstration pool from which in-context examples were retrieved and appended to the API documentations in the LLM's context. Evaluation metrics. The authors evaluated the models by matching the predicted API call against the ground truth. They reported the overall accuracy considering both API name and arguments correctness as the main metric, together with the percentage of examples with valid API calls and no syntax formatting errors, well-formedness, and the percentage of examples that correctly choose to use the ground truth API match. Results. The authors conducted comprehensive experiments and found that existing LLMs, including GPT-4 and open-source LLMs specifically fine-tuned for tool use, only reach a correctness rate in the range of 30% to 60%. However, the proposed STE method substantially improved tool learning for LLMs under both in-context learning and fine-tuning settings, bringing a boost of 46.7% to Mistral's Instruct 7b and enabling it to outperform GPT-4. Ablation studies. The authors conducted an ablation study for their exploration design, with exploitation done by fine-tuning Llama 2 Chat 7b. They separately ablated each key component of their exploration design and found that all components, execution feedback, short-term memory, long-term memory, and self-reflection, are essential for effective trial and error. Continual tool learning. The authors also explored continual learning of new tools and showed that simple rehearsal-based fine-tuning could enable continual learning of new tools with preserved previous skills. They randomly split the tools into 4 consecutive batches to simulate the continual setting. For rehearsal, during each round, they added 10% tool use examples for each API from previous batches into the replay buffer. The results showed that the model could drastically forget previously learned tools without rehearsal, but rehearsal largely mitigated this issue and allowed the model to continually learn new tools while preserving its previously acquired skills.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled LLM2Vec, Large Language Models Are Secretly Powerful Text Encoders introduces a novel unsupervised approach, LLM2Vec, which can transform any decoder-only large language model, LLM, into a powerful text encoder. The method consists of 3 main steps. 1. Enabling bidirectional attention. The first step in the LLM2Vec approach involves replacing the causal attention mask of decoder-only LLMs with an all-ones matrix. This modification allows each token to access every other token in the sequence, effectively converting the model into a bidirectional LLM. However, since the decoder-only LLM was not originally trained to attend to future tokens, this straightforward approach could potentially lead to suboptimal representations. 2. Masked Next Token Prediction, MNTP. To address the potential issue of worse representations, the authors propose a strategy to adapt the model to its bidirectional attention using Masked Next Token Prediction, MNTP. MNTP is a new training objective that merges next token prediction with masked language modeling. In this process, a portion of the input tokens is initially masked. The model is then trained to predict these masked tokens based on both past and future context. 3. Unsupervised Contrastive Learning, SimCSE. While the first 2 steps can transform any decoder-only LLM into an encoder for word-level tasks, they may not be sufficient for sequence representations. To address this, the authors apply unsupervised contrastive learning through SimCSE. In this step, an input sequence is passed through the model twice, each time with independently sampled dropout masks. This results in 2 distinct representations for the same sequence. The model is then trained to maximize the similarity between these 2 representations while minimizing the similarity with representations of other sequences in the batch. The combination of these 3 steps, enabling bidirectional attention, MNTP, and SimCSE, forms the LLM2Vec method. The authors demonstrate the effectiveness of LLM2Vec by applying it to 3 popular LLMs and evaluating the transformed models on English word and sequence level tasks. The results show that the models outperform encoder-only models by a significant margin on word-level tasks and achieve a new unsupervised state-of-the-art performance on the Massive Text Embeddings Benchmark, MTEB. The experimental work in the paper is divided into two main sections: unsupervised experiments and supervised experiments. These experiments were designed to validate the effectiveness of the LLM2Vec approach in transforming decoder-only large language models, LLMs, into strong text encoders. Unsupervised experiments. The unsupervised experiments were conducted on three popular LLMs, EST Llama 1.3b, Llama 2-7b, and Mistral 7b. The experiments were divided into word-level tasks and sequence-level tasks. Word-level tasks. The models were evaluated on three word-level tasks: chunking, named entity recognition, NER, and part-of-speech tagging, POS. These tasks were evaluated using the LLM2 benchmark. A linear classifier was trained on top of the frozen representations obtained from the last hidden layer of a model. The performance of the models was then compared to the LLM2V large, which is the current state-of-the-art encoder-only model. Sequence-level tasks. The models were also evaluated on the Massive Text Embedding Benchmark, MTEB, a collection of 7 diverse embedding task categories covering a total of 56 datasets. To select the best-performing pooling method for each method, ablations were performed on a 15-task subset consisting of representative tasks from each of the MTEB categories. Supervised experiments. The supervised experiments were designed to combine LLM2Vec with supervised contrastive learning. The models were trained on a replication of the public portion of the E5 dataset, which consists of approximately 1.5 M samples. The models were trained with contrastive learning using hard negatives and in-batch negatives. The training was performed for 1,000 steps with a batch size of 512. The performance of the models was evaluated on the full MTEB dataset. The models were compared to the unsupervised BERT models obtained from Jiao et al. 2021, and Echo embeddings, a concurrent approach by Springer et al. 2024. Results. The results of the experiments demonstrated that the LLM2Vec approach was successful in transforming decoder-only LLMs into strong text encoders. On word-level tasks, LLM2Vec transformed models outperformed strong encoder-only models by a large margin. On the MTEB, LLM2Vec transformed models set a new state-of-the-art for unsupervised models. When combined with supervised contrastive learning, LLM2Vec achieved a new state-of-the-art performance among models that train only on publicly available data.
Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.